Imagine standing on a beach or beside a quiet creek behind your home, with an ordinary handful of sand resting in your palm. It is dry, loose, and completely unstable, the kind of material that slips between your fingers and disappears with the first rush of water. Now imagine pressing two simple copper wires into that same sand after wetting it. There are no bags of gray cement powder, no thunderous concrete mixers, and no industrial kilns burning fossil fuels at a scorching 1450 degrees Celsius. There is only a mild electrical current, so gentle that touching the wires would produce little more than the faintest tickle. Then, within just a few hours, the loose sand begins to fuse. Right in front of you, it transforms into solid stone strong enough to carry a load. It sounds like a stage illusion, or perhaps a scene from an expensive science fiction film. But what if this process is not only real, but older than modern Portland cement? And what if certain quiet communities, including Amish stonemasons in Lancaster County, Pennsylvania, have been using a version of this technique for more than a century to grow their own foundations? Welcome back to The Roots Survived. I am glad you are joining me at the workbench today. For anyone new to the channel, this is where we search through the forgotten records of history, energy, and self-reliance to recover practical, affordable knowledge our ancestors used to build durable homes without depending on enormous industrial supply chains. Today, we are taking on one of the biggest materials of all: concrete, the substance supporting nearly every driveway, highway, and foundation in modern civilization. But we are also asking a question powerful enough to unsettle a $340 billion industry. Could concrete as we know it become completely obsolete? Stay with me, because before this video ends, I will guide you through a specific forgotten method described in a 1912 Bureau of Standards field report. It is a formula that was quietly pushed aside more than a century ago, and I will show you how it can be tried in a backyard or garage using little more than a 5-gallon bucket, wood ash from a stove, sand, and an ordinary car battery. Whether your goal is to make a garden path, form a footer for a shed, or even repair a cracking concrete foundation for less than $50, this is practical knowledge you can put to work. Let us begin. Section 1. The Sky's Hammer. Natural vitrification. To understand how electricity might transform loose sand into solid stone, we first have to look at the place where nature wrote the original rulebook, the violent heart of a lightning storm. When lightning strikes a sandy beach or a desert dune, it releases a tremendous burst of energy. At the center of the strike, temperatures can rise beyond 50,000 degrees Fahrenheit, roughly 5 times hotter than the surface of the sun. Ordinary silica sand melts at about 3,200 degrees Fahrenheit, so the sand directly in the bolt's path can vaporize almost instantly. As the current travels downward through the ground along the path of least electrical resistance, it fuses the surrounding grains of silica. The energy quickly fades, the material cools almost immediately, and a remarkable structure remains: a hollow, branching glass tube that can extend several meters beneath the surface like a frozen root system. These formations are known as fulgurites, a name taken from the Latin word fulgur, meaning thunderbolt. Some examples recovered from the sand dunes of Nebraska have measured as much as 15 meters long. Human beings have known about these strange glass structures for centuries. Ancient Romans regularly uncovered them after storms swept over sandy coastlines. Cicero used the striking expression condere fulmina, meaning to dig up thunderbolts, because people living near those shores understood, at least intuitively, that lightning could literally weld the earth together. Charles Darwin later wrote about fulgurites during his travels, and the explorer Alexander von Humboldt examined them in detail. For millions of years, nature has repeated this same experiment across sandy landscapes all over the planet. It demonstrates a basic physical principle. When intense electrical energy passes through silica sand, a loose collection of grains can be reorganized into a single glass-like structure. Yet for nearly 200 years, modern materials science mostly treated fulgurites as geological curiosities, beautiful examples of extreme natural power that could never be reproduced or scaled for ordinary human use. Researchers assumed that because lightning-level heat was involved, the phenomenon belonged to high-energy physics rather than practical construction. But perhaps they were studying the wrong side of the equation. What if 50,000 degrees were unnecessary? What if the silica did not need to melt at all? What if a small, gentle current could persuade minerals already dissolved in water to become the binding material, all at ordinary room temperature? Section 2. Whispers in the clay. Electroosmotic soil consolidation. The clue that moved this idea away from the blistering heat of lightning and toward the quiet flow of low-voltage electricity emerged during the 1930s. Geotechnical engineers were struggling with a stubborn problem: soft, waterlogged clay. Trying to build a dam, railway, embankment, or foundation on saturated clay is like building on jelly. The soil has very little shear strength. Under the weight of a heavy structure, it bends, shifts, and slides instead of remaining stable. Engineers discovered that something unusual happened when they installed rows of electrodes in wet ground and applied a mild direct current. The voltages involved were quite low, yet the effect was dramatic. At the boundary between wet soil particles and water, a natural electrical phenomenon called the double layer is present. The soil grains carry a negative charge, while the surrounding water behaves as though it has a slight positive charge relative to those grains. Once direct current is applied, the water trapped inside the soil pores is driven away from the positive electrode, called the anode, and moves toward the negative electrode, called the cathode. From there, it can be drained away. This method became known as electroosmotic stabilization. During the middle of the 20th century, engineers used it in major civil projects to stabilize weak slopes, excavations, and dam sites. At locations such as West Branch Dam, as well as unstable embankments across Europe and North America, low-voltage current was used to squeeze moisture from clay, reduce the size of the pores, lower compressibility, and greatly increase the soil's shear strength. But while reading engineering journals from the 1960s and 1970s, I kept noticing a detail that many authors treated almost like a secondary side effect. The electrical treatment did more than remove water. It also triggered long-lasting chemical and mineral changes inside the ground. Near the electrodes, the soil became permanently cemented. Electrochemical reactions reorganized the minerals, transforming soft clay and sand into a dense, rock-like hardpan that remained after the current was removed. Even so, the commercial construction industry remained focused on injecting huge amounts of Portland cement grout into the earth. As a result, this quieter form of electrically driven chemical stabilization survived mostly as a specialized technique for slope control. The possibility of using low-voltage current to grow construction material was largely ignored by ordinary builders. But beneath the warm waters of the Caribbean, a visionary architect was about to follow the same trail in an entirely new direction. Section 3. Ocean Builders. The Birth of Biorock. In 1976, German architect Wolf Hilberts imagined something that sounded as though it belonged in an eco-futurist novel. He wanted to create self-assembling, self-healing cities beneath the ocean. Rather than hauling enormous quantities of steel and concrete to remote coastal locations, Hilberts asked a different question: why not use the sea itself as the quarry? He understood that seawater contains a rich supply of dissolved minerals, especially calcium and magnesium. Hilberts found that when a metal mesh framework was submerged in seawater and supplied with an extremely low, safe direct current, electrolysis began to reshape the chemistry around it. At the negative electrode, or cathode, water molecules split apart. Hydrogen gas was released, while the local pH increased sharply and the surrounding water became highly alkaline. That sudden chemical change caused calcium and magnesium ions dissolved in the seawater to leave the liquid and crystallize directly onto the metal framework. Hilbert's called the material secrete, cement, or mineral accretion. Then, in 1987, he joined forces with Dr. Thomas Garreau, a brilliant Jamaican-born marine biogeochemist. Together, they recognized that this technology had an urgent purpose far beyond underwater architecture. It could help save dying coral reefs. They began calling the process Biorock because it did more than grow a hard limestone-like coating. It also had a profound, life-supporting effect on marine organisms. When a gentle current passed through steel rebar structures beneath the sea, a beautiful white mineral layer formed over the metal. Its chemical composition matched that of natural coral skeletons and the bright sands of tropical beaches. Corals transplanted onto these electrified biorock frames grew 2 to 10 times faster than normal. Even more remarkable results appeared during severe ocean warming events. In the Maldives during the catastrophic bleaching of 1998, when 95 to 99% of nearby natural reefs died, corals growing on charged biorock structures had a 1,600 to 5,000% higher survival rate. Why would electricity have such an effect? Every living cell spends a large share of its metabolic energy maintaining an electrical voltage difference across its membrane so that it can produce ATP, the universal energy currency of life. By surrounding coral with a mild external electrical field, operating in a safe, extremely low voltage range, the biorock process reduced part of that energetic burden. In simple terms, the corals received an electrical tickle. That left them with more available energy for growth, repair, and resistance to deadly heat. Over 4 decades, Hilberts and Garreau created more than 1,000 biorock structures in 45 countries, from Bali to St. Barthélemy. They proved that with roughly the electricity used by a couple of air conditioners, supplied by ordinary solar panels or wind turbines, solid limestone breakwaters could be grown directly in the sea. These structures bonded themselves to the ocean floor, strengthened over time, and survived Category 5 hurricanes without damage. While Hilberts and Garreau concentrated on coral reefs, one question remained unanswered. Could the same low-voltage chemistry be brought onto dry land and used by ordinary people to create their own structures? Section 4. The hidden 1912 footnote, Julius Weber, and the Amish foundations. If low-voltage mineral accretion works so well, why is it not common everywhere? Why do hardware stores still offer little more than heavy bags of Portland cement powder? To find an answer, we have to follow a scattered trail of evidence leading to a barn in Lancaster County, Pennsylvania, and to a faded footnote buried inside a public archive. Several months ago, while searching deeply through the archives of the National Institute of Standards and Technology, I came across a reference in a 1912 Bureau of Standards report, specifically Circular Number 22. During the winter of 1911, a field engineer named Julius Weber was working from the Pittsburgh field office. He had been sent into Pennsylvania Dutch country to investigate a mystery that had caught the Bureau's attention. Certain old barn and spring house foundations in the region were lasting 3 or 4 times longer than the modern commercial concrete structures around them. They showed no cracks and no spalling. When Weber spoke with local German immigrant masons and Amish builders, he learned that they were not using imported commercial cement. Instead, they relied on what they called the stone mix. The recipe was simple: local river sand, a small amount of ground burnt lime produced in a nearby kiln, and one carefully chosen secret ingredient: sifted hardwood ash gathered from the bottoms of cookstoves after a winter of burning maple, oak, and hickory. But the curing process was what truly surprised Weber. For silo piers and load-bearing cornerstones, the builders used a technique they called the current method. Copper wires were placed through the wet mixture inside wooden forms. The wires were connected first to glass dry cell batteries, and later to a small hand-cranked magneto, salvaged from an old Ford. A mild direct current then passed through the mixture for a full day and night, before the forms were removed. Weber's chemical analysis indicated that the low-temperature wood ash contained potassium carbonate, calcium oxide, and small amounts of silicates. When that ash was mixed with wet sand and exposed to a current of 4 to 12 amps at 24 to 48 volts, the potassium acted as a powerful catalyst. Crystallization accelerated by a factor of 10. A lime and sand mortar that would normally require months to cure passively became hard synthetic sandstone in less than 24 hours. Then the story takes a darker turn. Julius Weber recorded the formula in field notes, later referenced in a 1924 issue of Popular Mechanics. After that, the knowledge seemed to disappear. By the years following 1930, it had vanished from standard textbooks. Why? Between 1912 and 1934, powerful cement interests were strengthening their control over the American construction market around Allentown, Bethlehem, and Coppell, Pennsylvania. A quiet campaign began. Lobbyists pushed building codes from county to county, requiring inspected, permitted, or insured structures to use Portland cement. The American Concrete Institute, established in 1904, spent its first 2 decades promoting public campaigns against alternative regional masonry traditions that had already served communities for generations. The Amish masons did not hire attorneys or purchase advertisements. They simply became quiet. They continued building on their own land for their own families, while the rest of the English world grew increasingly dependent on bags of gray powder that cracked within 10 years. Section 5. Alchemy. In a 5-gallon bucket. The chemistry of sand and ash. Now let us pull back the curtain and examine what is happening inside that Amish bucket. You deserve to understand the chemistry behind the process rather than being asked to accept the story on faith. Passing direct current through a wet mixture of silica sand and wood ash effectively creates a small geochemical reactor. First, the electrical potential splits water molecules at the 2 electrodes. Around the positive electrode, the anode, the water becomes locally acidic. Around the negative electrode, the cathode, hydrogen gas is released, and the water becomes strongly alkaline, pushing the local pH into the range of 12 to 13. That highly alkaline range is where pozzolanic reactions can occur. Under these conditions, amorphous silica at the outer surface of each sand grain begins dissolving into the surrounding pore water. As it dissolves, it forms reactive silicate ions in solution. At the same time, calcium-rich wood ash and lime also begin to dissolve, releasing large quantities of calcium ions into that same water. Under ordinary conditions, those calcium and silicate ions would drift slowly through the mixture. Their movement would depend on passive diffusion, and forming bonds might require weeks or even months. But with direct current flowing through the material, the electrical field becomes a driving force. It steadily moves the calcium and silicate ions toward one another and speeds their migration through the wet mixture. When the ions meet, they combine to create calcium silicate hydrate, known throughout cement chemistry as CSH. Think carefully about what that means. CSH is the same binding phase, the mineral glue, that gives Portland cement its strength. It is the substance helping support skyscrapers, highway bridges, and airport runways. But instead of creating it by mining limestone, crushing the rock, and heating it inside a massive coal-fired kiln at 1450 degrees Celsius, you are growing it directly on a workbench. With sand, fireplace ash, and a small amount of electricity from a car battery, the entire industrial chain is bypassed. The direct current pushes the reaction deeply and evenly through the whole pore, producing a single solid mass of synthetic sandstone in 18 to 36 hours. As Eli Stoltzfus, a 71-year-old retired Amish stonemason, told me while I sat on his porch in Lancaster County, "We do not pour concrete, we grow stone." Section 6. Northwestern Spark. 2 volts to rebuild the shorelines. For anyone who thinks this is only old homesteading folklore, move forward to August 2024. In a peer-reviewed study published in Communications, Earth and Environment, a group of engineers at Northwestern University, led by civil engineering professor Alessandro Rota Loria, systematically demonstrated how low-voltage electrode position can harden marine sand into rock-like barriers. Professor Rota Loria was not trying to construct barns. His team was confronting a global coastal crisis. More than 40% of the world's population lives in coastal regions, while rising sea levels continue to destroy beaches. Traditional solutions often involve massive seawalls made from heavy stone. These barriers can cost millions of dollars per mile, yet they eventually fail because the sand beneath them erodes until the structures collapse. Another approach is to inject chemical binders into the seabed, but that method is extremely expensive and ecologically toxic. Rota Loria's team took its inspiration from oysters, mussels, and clams. These animals form shells from minerals already dissolved in the seawater surrounding them. They do not transport calcium from another location. Instead, they use metabolic energy to raise the pH in a small area and crystallize calcium carbonate. The Northwestern researchers inserted electrodes into sand saturated with seawater and applied only 2 to 3 volts, less than the combined voltage of 2 AA batteries. The current raised the local pH around the cathode. Almost immediately, calcium dissolved in the seawater began converting into solid calcium carbonate, or limestone. When the team increased the voltage to 4 volts, the reaction changed. Magnesium hydroxide and a mineral called hydromagnesite began to precipitate. These minerals formed directly inside the microscopic gaps between individual grains of sand. There they acted like a natural adhesive, locking the shifting grains into a stable and immovable mass. The most startling result was the estimated cost. Rota Loria's team calculated that electrically cementing 1 cubic meter of sandy ground costs only $3 to $6. Conventional chemical injection can cost as much as $70 for the same volume. That represents a reduction of roughly 90%, achieved with minerals already present in seawater and with voltage so mild that marine organisms cannot even feel it. The process offers another remarkable feature. It is fully reversible. If a coastal community later wants to remove the hardened material and restore the beach to loose sand, the battery connections can simply be reversed, switching the anode and cathode. The local pH then falls, and the current dissolves the deposited minerals back into the water, returning the sand to its original granular state without leaving a trace. In that sense, the system functions as a programmable, controllable, and entirely green engineering tool. Section 7. Growing Carbon Sink Structures. The CEMEX Coalition. While Rota Loria's team was using electrochemistry to weld coastal sand together, the researchers pushed the idea much further in early 2025. Working with CEMEX, one of the largest construction material companies in the world, they asked a bold new question. If rock can be grown in the sea, why not grow the sand itself? The world is currently facing a quiet but devastating shortage of suitable sand. Humanity consumes it in enormous quantities because sand represents roughly 60 to 75% of concrete by volume. To meet that demand, riverbeds, beaches, and marine habitats are dredged, often causing severe environmental damage. Rata Loria and Jeffrey Lopez developed a method using electrodes installed inside modular reactors supplied with seawater drawn from the shoreline. Carbon dioxide was captured directly from cement plant exhaust and bubbled through the electrified seawater. This altered the chemical balance and created bicarbonate ions. Those bicarbonate ions then reacted with calcium and magnesium already dissolved in the water, allowing the system to grow a sand-like construction aggregate. By changing the voltage and the rate at which carbon dioxide entered the reactor, the researchers could control the form of the particles. They could produce anything from lightweight, airy, porous flakes to dense, hard grains with sharp edges. This manufactured sand did more than replace material taken from rivers and beaches. It also acted as a major carbon sink. Because the particles were composed of calcium carbonate and magnesium hydroxide, 1 ton of the grown sand could permanently trap more than half a ton of carbon dioxide. When that aggregate was added back into concrete, houses could be constructed with a carbon-negative material capable of storing those emissions for centuries. Cemex and the Northwestern researchers did not stop there. They also reconsidered the way ordinary concrete is mixed. Traditional concrete carbonation attempts to inject carbon dioxide directly into a fresh concrete mixture. That process typically captures only 5 to 20% of the carbon dioxide and can reduce the strength of the final material. In June 2024, the team published another approach in communications materials called suspension carbonation. Instead of bubbling carbon dioxide into dry aggregate, they first introduced it into water containing a very small amount of cement powder. This produced a thin, carbonated, sparkling water and cement suspension. Because the liquid had such low viscosity, the chemical reactions happened extremely quickly. The team reported a carbon dioxide sequestration rate of as much as 45%. When this sparkling cement suspension was later combined with the remaining sand and gravel, the finished concrete showed no reduction in strength. In some laboratory tests, its compressive strength was actually greater than that of standard concrete. The material could still be poured into slabs, columns, foundations, and beams just like conventional concrete, while carrying nearly half its own weight in permanently locked-away carbon. Section 8. Your Backyard Stone Farm. Step-by-step die and cracked foundation cure. Now it is time to roll up our sleeves and move this idea out of academic papers and directly onto the workbench. I promised you a practical demonstration, so here is the step-by-step formula for growing your own stone over a weekend, with materials you can obtain for less than $40. You will need a standard 5-gallon plastic bucket to serve as the form. You will also need clean silica sand. A 50-pound bag of grade 20 silica pool filter sand can usually be found at a pool supplier or farm store for around $8. Do not substitute random soil from the yard. The mixture requires sand containing more than 90% silica for the reaction to work efficiently. Next, collect sifted hardwood ash. Use the fine white ash from a fireplace or wood stove and pass it through an ordinary window screen to remove charcoal fragments. Finally, obtain hydrated lime. A 50-pound bag can be purchased from many hardware or farm supply stores for about $6. Step 1. The mix inside the bucket. Combine 4 parts silica sand, 1 part sifted wood ash, and 1/20th part hydrated lime by volume. Blend all the dry ingredients thoroughly until the mixture has an even gray-brown color. Step 2. The water. Add water slowly while continuing to stir. The goal is a very particular consistency, similar to thick, warm oatmeal. Perform a squeeze test by taking a handful of the damp mixture and closing your fist around it. The material should hold its shape without releasing any water. If it crumbles apart, mix in a little more water. If it becomes soupy, add more of the dry sand and ash blend. Once the consistency is correct, pack the oatmeal-like material firmly into the bottom of the bucket. Step 3. The electrodes. Take 2 ordinary half-inch copper pipes, each approximately 18 inches long. Push them vertically into opposite sides of the wet mixture, leaving about 10 inches between the pipes. Roughly 4 inches of each pipe should remain above the surface. Step 4. The power connect the positive terminal of a 12-volt car battery, solar charge controller, or benchtop direct current power supply to one copper pipe. This pipe becomes the anode. Connect the negative terminal to the second pipe, which becomes the cathode. Almost at once, you should hear a very soft hissing sound. Tiny hydrogen bubbles will begin appearing around the negative electrode. Within about an hour, the bucket may feel gently warm. That warmth means the electrolytic reaction is proceeding perfectly. Step 5. The cure. Allow the current to flow continuously for 18 to 24 hours. Do not stir the mixture, add more water, or disturb the bucket during this period. After 1 full day, disconnect the battery. Wait another 2 hours, then carefully cut away the plastic bucket using a utility knife. Inside, you should find a solid cylinder of synthetic sandstone that feels cool to the touch and reaches 3,000 psi. Strike it with a hammer, and, rather than crumbling, it should ring like naturally formed geological stone. Scaling the process up. To create a larger shed footer or garden path, the same geometry can be expanded. Construct wooden forms from standard lumber. Then arrange copper pipe electrodes in a grid, spacing them about 18 inches apart in both directions. Connect alternating rows to positive and negative bus wires running along the top of the form. For an off-grid project, the system can be powered by a small solar array, or allowed to run from Friday evening until Sunday morning, just as Eli Stoltzfus said his father once did before church. The under $50 foundation repair method. Suppose you own a house built before 1980, and the concrete foundation around the basement or crawl space has begun cracking, crumbling, or allowing water to enter. Many contractors may recommend jackhammering out the damaged section, with a repair estimate ranging from $10,000 to $30,000. Instead, use the method engineers applied in a 2003 Auburn University field trial involving marine structures. Build a simple wooden frame and pack wet silica sand tightly against the damaged and cracked concrete. The sand should be mixed with salt water, prepared at a ratio of approximately 3 tablespoons of non-iodized salt for each gallon of water. Place 1 electrode into the wet sand pack. Drive a metal rod into the nearby soil to serve as the ground electrode. Connect the system to a standard 12-volt trickle charger and allow the current to run for 3 to 7 days. The low-voltage field forces calcium and magnesium dissolved in the salt water directly toward the cracks in the foundation. Those minerals then deposit inside the pore network of the concrete, growing calcium carbonate limestone from the interior outward until the cracks are permanently sealed. The repaired area becomes harder and denser than the surrounding 90-year-old concrete, while the materials cost less than $50. Conclusion. The roots survived. When you lift that cool, heavy piece of stone from your workbench, a stone you grew using river sand, fireplace ash, and an ordinary car battery, something inside your thinking begins to change. You start to question the story repeated throughout our lives, that Portland cement is the only serious material for building a foundation, and that every alternative is merely folk superstition. That story was shaped by marketing departments and lobbyists more than a century ago. It was designed to lock people into a cycle of constant purchasing, forcing them to buy bags of gray powder that might fail within a decade, while ignoring the materials and energy already available on their own land. Recovering this simple electrochemistry is not only about saving money on cement or avoiding an expensive foundation repair. It is about cutting one more wire of dependency. It means reclaiming a piece of rugged, resilient American engineering that was quietly buried so someone else could profit from its disappearance. Now I want to hear from you. Have you ever stood beside an old Amish foundation that remained solid and uncracked? Or are you planning to try growing a piece of stone this weekend? Share your experience in the comments and begin the conversation. This community needs to hear your story. And if you want to continue down this path with me as we recover the roots of self-sufficiency, make sure you subscribe. Next week, I will show you how families in Holmes County, Ohio, keep their root cellars at a steady 52 degrees all year without using a single kilowatt of electricity. They do it with a simple passive ventilation design traced to a Swiss farming manual published in 1847. You will not want to miss it. Go grow some stone, take care of your land, and always remember, the roots survived. I will see you next week.